Alright, so we're finally to the point where we're focusing on APC materials specifically. So, APC, hello again. Broad review of many of the topics you need. It doesn't hurt for you to take a look at the other videos that we have up there. Of course, you can skip fluids, you can, skip thermo, you can skip modern, and I think that's pretty much it. It turns out APC is kind of a dense course. A lot of material to cover and a lot of in-depth information. That is why technically it is supposed to be a kind of 2-year course. It's a 1-year course, but it's heavily suggested that you have an intro physics class before that to kind of give you the broad strokes of what's going on. Regardless, let's pick up. So, APC, we're going to take a look at calculus in the mechanics side. Alright. Key things. I'm going to go through and I'm going to put down a bunch of calculus relationship equations. For the most part, you want to make certain that you're familiar with most of them. The first few that I put up are the absolute most important. Make certain that you know these, if nothing else. But the others are still pretty useful too. Most important are your differential relationships for kinematics. Alright, so for kinematics, simply v equals dx dt. And acceleration equals dv dt. Be familiar with those. These guys are kind of the key to doing a lot of that. Technically, if you're familiar with it too, doing separation of variables, we can do dt, dt, and we end up with x is going to be equal to the integral of v dt. And v is going to be equal to the integral of a dt. Technically, these guys are all vectors, though usually they're done in one dimension for us because, yeah, multivariable calculus is not something that we have to deal with, at least as of now. Know these relationships. For the most part, I recommend making certain that you're very comfortable with these. They're going to be the more common replacements that you have to make. Pardon me. But also be familiar with how to get them in their integral form because that can be useful. Especially if you can use it as a means of reminding yourself how to do separation of variables so that you can get this form. Because separation of variables is how you go about normally evaluating all of our integrals. Okay, so that's kinematics. Those are key. Learn those. The other one that I feel is just too profoundly important to take anything, any physics calc based at all without knowing is this one, the work equation. Now remember that this is work equals the integral of f dot dx. Both of these guys are vectors, but work is basically a means of transferring energy from one place to another, and work and energy are always scalars. They are not vectors. They do not have direction. This dot product eliminates that direction. In fact, this simplifies down to, one of its most simplest forms, f delta x cosine theta. Always remember that you have to be applying this force over a distance, and that your angle is important as well. Okay? So double check that. But this relationship is incredibly important. Now from this, there's one thing that we did talk about a little bit. And that is, when we first introduced work-energy theorem, I told you that when I do work on this, I lift this guy up, and it doesn't end up with a whole bunch of kinetic energy because gravity totally stole my work. This brings up an important relationship that isn't gotten across as well as it should be. Work is nothing more than negative potential energy. Or phrased differently, potential energy is nothing more than negative work. Gravity and other conservative forces, things that we apply a potential energy on, all they're doing is doing work. They're applying a force over a distance, and they have a tendency to, when I put work into this, they steal it, but they give it back. They do predictable work. However, what they do, we put this negative in here because while gravity is stealing the effort that I put in, the energy that I put into this, it's storing it so I can get it back. So what we did when we encountered this, and we realized that things like gravity and springs, and electricity for that matter, do predictable work. They steal our energy, but they give it back. we simply labeled it a new type of energy, a place where that energy gets stored, because it saves us the time and trouble of finding the work every single time. We called that a potential energy. Now because of this, we end up with, if you can remember this and this, that leads to a pretty fundamental equation, which is good to keep on hand. I'm going to double check it so I don't have this wrong, but our force equals negative the derivative of our potential energy with respect to x. Or conversely, our potential energy equals negative integral f dot dx. In other words, here's our work, negative, bingo, it's this equation all over again. One final thing that I will note, we used PE all the time in class to try and give something where it's easy to remember that it's potential energy. In many other places, textbooks and so forth, instead of potential energy, PE, they will call it U, capital U. So, oftentimes you will see this as du dx. Don't forget that negative. Okay? Profoundly useful. These are really, really key. And so we're almost done with the calculus for mechanics stuff. And so you can see this isn't that much. Get a good idea on these and how to apply them. A couple of the final things that I want to include is Newton's second law in calculus form. The sum of forces equals dp dt. This is what Newton originally said. Now, we did a few things where if you apply chain rule, where this is our mass and our velocity, and you separate it out, as long as your mass isn't changing with respect to time, then yes, this does end up simplifying down to ma, where that's our mass times dv dt, right? That's that relationship way back up here. So, but it doesn't hurt being familiar with this, because sometimes you'll have questions that deal with forces and changes in your momentum, and this can be a very good way of dealing with it. Now the other way of keeping track of that, kind of the inverse of this, is something we call impulse. Now in class we used a capital I, though the standard, at least what I've been seeing more and more, is a J. So capital J equals the integral of f dt. There's no dot this time because the direction of our force is also the direction of our net impulse. Now just like the non-differential form that we saw in APB, this is also going to be equal to our change in linear momentum. That's the same impulse there. But we can see that there's a relationship with our impulse from this, where now I would take my dt, move it over there, and I end up with the integral of f dt equals my change in momentum, because I would integrate dp, and I would integrate it from my initial momentum to my final momentum, and then evaluating that integral, it's final minus initial. Bam. Delta p. Alright. That's pretty much it. That is all of mechanics. I don't think I'm overlooking anything important, but that is all of mechanics calculus-wise in a nutshell. Big things? These guys definitely, because most of your differential equations are going to come from them. Also, know the equation for work, because it's just too useful. Also helpful are going to be these guys here. And then finally, these are going to be very helpful as well, but they're lower on the list. It pains me to say that Newton's second law in its proper form is lower on the list, but it is. Conceptual. Conceptual. Main thing to take a look at on this is going to be your key to setting up the calculus here is pretty much always going to be on simple replacements, or what I consider simple replacements. Your mileage may vary, but simple replacements. You're going to have something where you're going to set up your sum of forces, where it's going to be equal F1 minus F2 or something like that. And you're going to set it equal to your mass times your acceleration. Newton's second law at work. Then the next thing you're going to do, so that you can actually get some calculus out of this, which is the point of the class, F1 minus F2 equals mass times, you guessed it, dV dt. Simple replacements. Those equations that I told you at the top, very important. That's because they're usually the key to swapping these out. In fact, let's take a look at a very specific one, the type of question that comes up a fair amount for calc-based physics. Drag. we're going to have, pardon me, we're going to have, say, an object falling, and it's going to be subject to a drag force. So we have mg, and we have some drag force, F sub d, where F sub d, we're going to say, is going to be equal to some constant times, we'll go with velocity squared. Why not? So, we want to find out something about the velocity as a function of time, basically how fast this thing's going to go. All right. Sum of forces. In this case, I only need to look in the y because that's all that's going on. I'll have drag force minus mg equals ma. My drag force was b v squared minus mg equals m, wait for it, dv dt. Bingo! That right there is a differential equation. We have a bunch of constants. B is a constant, mass is a constant, acceleration due to gravity is a constant, mass is a constant again because I'm redundant. And the only other things are v and how it changes with respect to time. That is a differential equation. If that's all they're looking for, if that's all I'm asking for, you pretty much can leave it in that form. Now you can clean it up a little bit. We've seen that this becomes a bit of a mess, at least in the form that I've got here. If you have to solve it, you want to try and get your v and your dv on one side and everything else to the best of your ability over on the other. If I take a look at this, it's going to be something along the lines of, let's see. Knew I should have written this out more clearly. Let's see. So I can have bv squared equals m dv dt plus mg. That may not have been the best move there. But let's see. Yeah, because I need to get that divided over. So what I'm going to do is I'm going to divide both sides by my mass. So I'm going to have b over m equal, or times v squared equals dv dt plus g. And then I'm going to have b divided by m equals dv dt times 1 over v squared plus g over v squared. This one gets a little unpleasant. I think that's why I ended up avoiding this one before. But we get all of this together. This one you often solve by setting up a final velocity, a terminal velocity, which we're going to have with setting our forces equal to each other. We find where our acceleration is canceled out. And so drag force will be equal and opposite to our gravity. So we're finding where this guy is equal to 0. I'll have to check my notes. I had not put them fully together for the drag problem, so I apologize. But for the most part, this guy here is your differential equation, which is what you're shooting for. We had similar ones where we found the charging and discharging time of capacitors. And so this is going to be equal to my drag force, which is b v squared. And so solving for my terminal velocity, it is going to be mg over b square root. So I'll divide both sides by b and then take the square root. That'll be my terminal velocity. That comes from this point where these guys are equal, and that happens when my acceleration is 0, so this is the final velocity that it will actually have there. We end up using this to parameterize up here and clean this up a little bit, but this guy is not a pleasant integration any way you look at it. Okay, some of the final things are going to be, again, simple replacements. They may do something like give you the position function as a function of time equals 3t squared plus 2t plus 1, right? And they want to find, they ask you for, say, the kinetic energy. Well, kinetic energy is equal to 1/2 mv squared. So maybe they want you to find the kinetic energy at time 2 seconds. Okay, well, I will take that my velocity equals dx dt. I take the derivative of this guy with respect to time, and I find that I've got 6t plus 2. That's my velocity. So I'm going to square this for v squared, multiply it by my mass, and then plug in 2 for t and solve for that. They may ask you for the momentum at a given point. Again, find your velocity. Momentum equals mv. They'll likely give you the mass. I will likely give you the mass as well. although I have forgotten it from time to time. All right, so you do that. Maybe you want to find the net force on something. Well, the net force is going to be equal to MA. Oh, there went my marker. Is going to be equal to MA. You take your x, you take the derivative, here's your velocity. So my velocity is 6t plus 2. I'm going to find my acceleration, which will be the time derivative of my velocity, which is going to be 6. My acceleration is a constant, 6 in this case. Again, it's all kind of simple replacements. If you know way back up here, these guys, a lot of it's going to simplify down to that. The other stuff is mostly built around energy, so knowing your work and your relationships here are going to be key. That's pretty much all of it.